In this video, we will discuss the basic structure of simple mathematical proofs, and we will see how to disprove a mathematical statement using a counterexample. We begin by precisely defining the familiar terms odd and even and prime and composite, and then discuss how to prove or disprove mathematical statements involving these terms. Let's start by defining even and odd. An integer n is even if and only if n is twice some integer. This means that n is even if and only if there exists an integer k such that n equals 2k. An integer n is odd if and only if n is twice some integer plus 1. That is, n is odd if and only if there exists an integer k such that n equals 2k plus 1. Let's think about a couple of examples. First of all, 10 is even. This is because using k equals 5, we see that 10 is 2 times 5. Also, 0 is even. This is because taking k equals 0 gives us 0 equals 2 times 0. The integer 13 is odd because 13 can be written as 2 times 6 plus 1. Also, the integer 1 is odd, and this is because we can write 1 as 2 times 0 plus 1. Next, let's define the terms prime and composite. An integer n is prime if and only if n is greater than 1, and for all positive integers r and s, if n equals r times s, then r equals 1 or s equals 1. An integer n is composite if and only if n is greater than 1 and n equals r times s for some positive integers r and s where r is not equal to 1 and s is not equal to 1. Let's write out symbolically the definition for n, an integer, to be prime. So we write it out symbolically and notice that this says exactly the same thing we said in the definition. Also, we can do the same thing for composite. So n is composite if and only if, and we write out the definition symbolically, and again, this says the same thing as the definition. Something to note is that the integer 1 is neither prime nor composite, and in fact, the definition for prime and composite holds for integers which are greater than 1. Now let's think of some examples. The integers 2, 3, 5, and 7 are all prime. On the other hand, the integer 9 is composite because 9 is equal to 3 times 3. So here r would be 3 and s would be 3, and neither of those is equal to 1. Also, the integer 30 is composite because 30 equals 3 times 10. Notice that you could have also said it's because 30 equals 5 times 6. You don't need to write out all the different ways that you could do this. Finding a single r and s, which are both not equal to 1, such that they multiply to give n, is enough to show that it's composite. Observe that an integer n which is greater than 1 is either prime or composite, but not both. This is because the condition for being composite is the negation of the condition for being prime. Just take a look at the symbolic representation of the definitions. Now, let's start our discussion about proofs of mathematical statements, and we begin by discussing how we can prove an existential statement. To show that the statement, there exists x in D such that p of x, is a true statement, it is enough to find one example of an element x in D for which p of x is true. As an example, let's say that we would like to prove the following mathematical statement. There exists an integer x such that x is greater than 30 and x is composite. Notice that here the predicate is x is greater than 30 and x is composite, which is a conjunction. Because this statement is an existential statement, it is enough to find a single example of an integer x which satisfies this predicate. So here's our proof. We take x equals 32. Then 32 is greater than 30, and 32 equals 2 times 16, where 2 and 16 are positive integers, and neither one of these is equal to 1. This means that x equals 32 is a positive integer which is greater than 30 and is composite. So we have completed the proof. Placing a square at the end of a proof is something that mathematicians do to denote that this is the end of the proof. It is used in place of the traditional abbreviation QED, which stands for the Latin phrase quod erat demonstratum, which translates to that which was to be demonstrated. It is important for a reader to understand where the beginning and end of a proof is. This is why we write proof at the beginning and use a square at the end. Next, we will discuss the method of direct proof of universal statements. In particular, one way to show that the statement for all x in D, P of x, is true is to use a direct proof. The first step is to say, suppose x is an element of D. The second step is to show that P of x is true. In the first step, it's important to observe that x is an arbitrarily chosen element of D, so we cannot assume anything about x except that it is an element of D. For example, if D is the set of all integers, we would begin by saying, suppose x is an integer, and we would not make any further assumptions about x. Step 2 was to show that P of x is true. This is done using definitions and previously established results, as well as the rules of logical inference. Now, one of the most common statement forms that we aim to prove in mathematics is the universal conditional statement. So let's discuss the method of direct proof for showing that a statement for all x in D, if P of x, then Q of x, is true. Step 1 is to suppose that x is an element of D and P of x is true. Step 2 is to show that the conclusion Q of x is true, and this is done using definitions, previously established results, and the rules for logical inference. So now, let's prove a statement of this form using a direct proof. In particular, we will prove the lemma, for all integers n, if n is odd, then n squared is odd. Let's make a quick remark about the term lemma. You will often see a mathematical statement being called a lemma, proposition, theorem, or corollary. We use the term theorem to denote a mathematical statement which is true and has mathematical significance. The terms lemma and proposition are also used to denote true mathematical statements, although these usually have less high importance. Often in mathematics, one or more lemmas are first proved, and then those are used to prove a theorem. The term corollary denotes a result which follows almost immediately from another result. So now let's go ahead and prove this lemma by direct proof. Our first step is to say, suppose n is an integer and n is odd. So we've done the first step of a direct proof, but now what can we get our hands on? Well, we know that n is odd, so we can use the definition. We will say, then by definition, n is equal to 2k plus 1 for some integer k. Hence, n squared is equal to 2k plus 1 all squared. So we can expand this out and rewrite this as 2 times 2k squared plus 2k plus 1. Now, why is it useful to write out n squared in this way? Well, here we can see that since k is an integer and 2 is an integer, 2k squared plus 2k is also an integer. Here we assume familiarity with the basic properties of integers, such as the sum of two integers is an integer, the difference of two integers is an integer, and the product of two integers is again an integer. What does this all mean? Well, it means that there exists some integer L such that n squared equals 2L plus 1, and therefore by definition, n squared is odd. So what we have just demonstrated is that if we take any odd integer, its square is odd. So we'll conclude our proof by saying, therefore, the square of an odd integer is odd, and this completes the proof. Now here are some tips for how to write a proof. Begin by writing down the theorem that is to be proved. Next, clearly mark the beginning of the proof with the word proof. Make sure to use precise definitions of any mathematical terms. Also, write your proof in complete sentences, which can be a mix of English words and symbols. Give a reason for each assertion in your proof. For example, you may say something is by definition, or by a previous theorem. Make your proof self-contained. In particular, Clearly explain the meaning of each variable that you use in your proof. Also, make sure to display equations and inequalities clearly. And finally, make sure that you conclude by stating what it is that you have proved. It is important that you believe your proof, and also that somebody reading your proof would become convinced as well. Of course, not all mathematical statements are true. A mathematical statement can be disproved by finding a counterexample. In particular, to show that the statement, for all x in D, if p of x, then q of x, is a false statement, find one value of x in D for which p of x is true and q of x is false. This is called a counterexample. So finding a counterexample for a statement proves that the statement is false. Here is an example statement. For every integer n, if n is even, then n divided by 2 is even. Here is a counterexample to this statement. Take n equals 6, which is even because 6 equals 2 times 3. But now, n divided by 2, which is 6 divided by 2, equals 3, which is odd because 3 is equal to 2 times 1 plus 1. Since we found a counterexample, this statement is false. Notice that we didn't have to take n equals 6. There are other counterexamples that you could have chosen. But finding a single counterexample is all you need to disprove the statement. Here is another example of a statement of this form. For every integer p, if p is prime, then p plus 3 is prime. Here is a counterexample to this statement. Take p equal to 3, which is prime. Now, p plus 3 is equal to 6, which is composite because 6 equals 2 times 3. Therefore, the statement is false. So in this video, we have seen that one way to show that a universal conditional statement is true is to use a direct proof. We have also seen that to show that such a statement is false, we just need to find a counterexample.